Next, we're going to talk about maximum likelihood estimation. And what this statistical method gives us is a general way to estimate parameters. So, for example, let me get my red pen out here. Now, we've talked about a population mean, mu, a lot. And the statistic then that we used to estimate it was a sample mean, denoted by y bar is equal to sum of the y's over n. And this statistic, this estimator, was introduced by intuition in terms of it makes sense to use a sample mean to estimate a population mean. Also, we gave some further justification for using this sample mean to estimate the population mean by showing that the expected value of y bar is equal to mu. Thus, y bar was an unbiased estimator. Excuse me. Now, we've also talked about using the sample variance to estimate the population variance as well. And this was somewhat introduced by intuition, where we take the sum of these y's, subtract them off from y bar, square them every time, and then sort of get an average value, where we divide by n minus 1. And this was further justified by finding the expected value of s squared was equal to sigma squared. Thus, s squared is an unbiased estimator of sigma squared. But let's say we have the following situation instead. Suppose we have y1 through yn as a random sample from a population characterized by this particular PDF. Notice the y's are between 0 and 1. And we also have this parameter beta. And as we've seen before with probability distributions, this parameter is going to control the shape of the PDF. Do also note that I just have this written as in terms of f of y. And this is just an easy way to say, okay, these y's have this corresponding PDF. If one wanted to, I could have wrote it as f of y sub I for I equal 1 to n. Note that this parameter is going to be greater than or equal to 0. This is another one of these named probability distributions. This is actually a beta probability distribution. And so you might be wondering, well, does it really matter what I use for an estimate of beta? Let's take a look at some plots. So what we see here is when beta is equal to 1, and again, y ranges from 0 to 1, we just have this kind of flat line. In fact, this is actually a uniform PDF. But as beta changes from 2 to 5 to 10, we can see that the shape of the PDF changes. And so because of that, we can say that indeed it's very important to understand what beta is, because that will totally change your understanding of how a particular population is being characterized by this PDF. So, what then statistic from taking a sample should we use to estimate this beta? And just from looking at these plots, just from looking at the PDF itself, it's not really clear how can I use information from my sample to estimate this beta in terms of what will be a nice expression for what beta should be. And in fact, what one could do is actually do derivations, which we will talk about shortly, or a method to do the derivation shortly. And this is what one can come up with for that estimate for beta. And we put a hat on top of beta to say that this is an estimate. And so that estimate is negative n over the sum from I equal 1 n of the natural log of 1 minus, and that should be y sub I. Just from looking at the plots, just from looking at the PDF itself, I don't think any of us would have thought, yeah, that would be a nice estimator to use. But in fact, it is. As we will talk about shortly here, this ends up being a maximum likelihood estimator for beta. Okay, So in some cases, there's intuitive ways to estimate the parameter. In other cases, like this one, there isn't. And so the most common method that people use to find estimators, I should say most general method, is what's called maximum likelihood estimation. This leads to a maximum likelihood estimate. And this estimate is going to be based upon sampled values. Now, to help introduce it, let's talk about an example. This goes back to us talking about field goal kicking. And this, as we've seen before, the success or failure of field goal can be modeled by in this case, we're going to use a Bernoulli PDF. So, if I go out and kick a field goal, I get either 0 or 1, 0 for failure, 1 for success. That's going to be, let's say, my y sub 1. And that can be modeled by a Bernoulli PDF. I go out and kick another field goal. Again, y sub 2 then would be 0 or 1 for failure or success. And let's say that the probability of success on every single kick is the same. So I'm doing these kicks under similar circumstances, and this probability of success is denoted by the Greek letter pi. Here's what the actual PDF would look like for this particular Bernoulli PDF. In this particular case, I did write it in terms of the y sub i's, but I could just use y itself, as long as you realize that, okay, this is for all the possible y's that you could have. And let's suppose then that we take a sample of field goals, and we denote then the corresponding random variables for these results as y1 through yn. Since this is going to be a random sample, each of these y's are independent of one another. And so with this, what we can do is that we can summarize what's going on here by finding a joint PDF. And so if I look at the PDF of f of y1 through yn, this is going to be equal to f of y1 times f of y2 times all the way up to f of yn. The reason being is because these y's are independent of one another. And so I can work with these marginal PDFs. Now, one can write the product of all these f of y's in a simplified form using a product notation. So we've seen, obviously, summation notation, such as the sum of y sub I equal 1 to n of y sub I. That's just y1 down to yn in terms of the sum. Instead, one could use a product notation, which is typically uses a capital pi symbol. This has nothing to do with the pi's that we have there. And we have the product from I equal 1 to n of y sub I is just y1 times y2 times all the way to yn. And so I can write this now as the product from I equal 1 to n of f of y sub I. What is f of y sub I? Well, I can just put in my Bernoulli PDF there. And then we have a little bit of simplifications that can occur. So for example, if I have, let's say, 2 raised to the 3 power times 2 raised to the 5 power, of course, this is 2 raised to the 3 plus 5 power, or in other words, 2 to the 8th power. Using that same idea then, since I'm taking the product of all these PDFs, now I have pi raised to the sum from I equal 1 to n of the y sub i's. And I take that times 1 minus pi raised to the power of n minus the sum of these y sub i's. Make sure you do understand that. So that's my joint PDF. Now, our goal is to use information from our sample to estimate pi. So now we're going to, let's say, change our notation a little bit. We're going to say that this joint PDF is now what's called our likelihood function. And we write it as a capital L. It's a function of pi. And then I have that vertical line there to mean a similar thing to what we've seen before, where it's like it's the word given. So I have this likelihood function L, that's a function of pi, given my observed data values, y1 through yn. Again, this is called a likelihood function. What this likelihood function then is going to allow us to do is, given our observed data, it's going to measure for us what are the most plausible values for what pi would be, again, given the sample that we have. So let's say I observe 4 successes. Just to, I guess, make things a little bit easier to write, suppose W is the sum of the yi's, the number of successes. And what we're going to do is plot the likelihood function. So I have the sum of the y sub i's with the W. I have n, and let's look at different possible values of pi. First, we're going to look at in terms of a table before the plot. And so I'm going to look at a pi of 0.2, pi of 0.3, and all the way to 0.5. I'm going to combine these together into a vector, which I call pi. And then my likelihood function, I just write it out in the corresponding syntax for R, and this is what we get. So when pi is 0.2, my likelihood function is 0.0004. When it's 0.3, it increases. When it's 0.35, it continues to increase. It increases all the way up to when I have pi equal 0.4. Then it starts to decrease again. And this is a plot of that likelihood function. Now, the way that maximum likelihood estimation works is that the most plausible value for your parameter is the one that maximizes the likelihood function. In this particular case, we can see that at pi equal to 0.4, that's where I reach the top of that curve. And that's what's called then my maximum likelihood estimate, pi equal 0.4, because it maximizes my likelihood function. We'll relate this back to what a joint PDF was for us. So pi equal 0.4 is the most plausible value of pi. Since this is actually an estimate, rather than calling it pi itself, we're going to call the maximum likelihood estimate pi hat. Now, when you took a calculus, and we've done calculus before, you've learned about how to maximize a function relative to some, let's say, variable of interest. Here we can apply those same techniques that you would learn in a calculus class to now, instead of having to do this plot or construct this table, we can come up with a general form for what this maximum likelihood estimate would be. And before I do that, I just want to mention to you, notice we had 4 successes out of 10 trials. And I apologize if I didn't mention before that we had 10 trials there. And what have we used before for a proportion to estimate pi? Well, we used the Stanford proportion. We used 4 divided by 10, or 0.4. And this maximum likelihood estimation ends up giving us the same result. So it's quite intuitive there. It makes sense to use the number of successes out of the number of trials as a way to estimate pi. Okay, sorry for having to go back. So let's talk about then the general way using calculus that we can find that maximum likelihood estimate. The value of pi that maximizes our likelihood function. So the first thing that we're going to do, and while we don't need to do this step, we're typically always going to do it because it makes the math work a lot easier. The first thing that we're going to do is we're going to find the natural log of the likelihood function. And note that whenever in statistics you see log there, and obviously there's other, there's log base 2, there's log base 10, there's a whole bunch of other ways to use a logarithm. Typically in statistics, whenever you see log, that will mean natural log. So please realize that. So we take the natural log of the likelihood function. And then what we're going to do is, again, remember, we want to maximize this likelihood function. And if I maximize either the likelihood function directly or the log likelihood function, it's not going to matter because the log transformation is a monotone transformation. So always we'll get the same answer in terms of what the value of, in this case, pi, it actually maximizes it. Next, what I'm going to do is take the derivative of the log likelihood function with respect to pi. And then I'm going to set this derivative equal to 0 and solve for pi to find the MLE, maximum likelihood estimate. The solution is the value of pi that will maximize this likelihood function, provided certain general regularity conditions hold. You don't worry about those for our class. They will always hold for us. And do note that this ends up being the maximum rather than, let's say, the minimum, because of how we end up working with probability distribution. So in calculus, you'll learn, okay, this will either be a maximum or minimum. For us, it will always be a maximum. Okay, so let's actually go through then the details of using calculus here relative to this likelihood function. So I first take the log of the likelihood function, just to review some properties of logarithms. If I have the natural log of a times b, that's going to be log of a plus the log of b. Also, if I had the log of, let's say, c raised to the d power, I can rewrite this as d times the log of c. Just basic review of logarithms. And so I'm going to apply those two properties, you could say, to working with this likelihood function. So log of, here's my likelihood function. Now notice how this part's up in a power. That's why I brought it out. This part's up in a power. That's why I brought it out. And notice how I'm taking the product of these two quantities there, pi raised to a power times 1 minus pi raised to the power. So that's why I can separate this all out by a plus sign. Then what we can do is we can take the derivative with respect to pi. So of course the derivative of log of pi is 1 over pi. Derivative of log of 1 minus pi is negative 1 over 1 minus pi, because I had the chain rule going on there. I set then this derivative equal to 0, solve for pi, and if you go through all the math, you get pi is equal to the sum of the y's divided by n. In other words, the number of successes divided by number of trials. Before we had 4 successes, 10 trials. 4 out of 10, or 0.4, was our maximum likelihood estimate. And so this is the general way of finding that out. And again, this is quite intuitive. This estimate we will refer to as pi hat, again, to help us avoid confusion between what the parameter is and then what its corresponding estimate is. Okay, so this is how you would go through doing this by hand. How could I use Sage to do these calculations, to derive the maximum likelihood estimate? So what I can do is this. Again, I'm going to declare n as, in Sage's terminology, as a variable. But I'm also going to do this with I, because remember, I have to deal with y1 through yn, or in other words, y sub I for I equal 1 to n. And in order to actually tell Sage that I do have this y1, y2 up to yn, where I'm going to index it by I can use the following syntax. Y is equal to a function, y, and then the parentheses, I. And so when I just type y itself, we can see that Sage says, okay, that's y with essentially a subscript I. Next, what I'm going to do is type in my log likelihood function. So to do the natural log in Sage, I can use the log function itself. To do the summation, we've seen this before, I use the sum function. And notice how I have a y parentheses I in there. I am summing from I equal 1 to n, plus log of 1 minus pi times n minus the sum y sub I there. Okay. And I don't know why Sage does this. For some reason, it wants to turn around 1 minus pi to be minus pi plus 1. It's the same thing, but for some reason it always wants to do that. Next, what I do is I take the derivative of the log likelihood function with respect to pi, and the way I do that is use the diff function. And this is the derivative there. You can match it up with what we had previously. And then I want to set this equal to 0, solve for pi. And the way I do that is I use the solve function. Notice I'm saying I want to solve this equation. It's going to automatically be set equal to 0. Solve it with respect to pi. And when I do this, I get what I had before by doing it by hand. This is, again, Sage's syntax. Again, the sum of the y sub i's divided by n. Okay. Well, this pi hat can be derived from a binomial PDF point of view as well. So let's say that W is our number of successes, and I have n trials. Just to show you that you get exactly the same thing because of the relationship between a Bernoulli and a binomial, let's just quickly go through some stuff here. So here's my PDF. And notice in this particular case, I'm just observing essentially one outcome for my PDF. I'm not having, let's say, one Bernoulli times another Bernoulli times another Bernoulli to get my joint PDF. Here, I just have a PDF, number of successes out of number of trials. And so my likelihood function ends up being L of pi given W, just my PDF. And so now when I work within the logarithm of my likelihood function, look what happens. I have 3 separate terms. We essentially had these last 2 terms previously when we were working with the Bernoulli case. But now we have this extra part here dealing with the combination. But when I take my derivative with respect to pi, look what happens here. That part disappears because pi is not in it. The derivative of the log of n choose w is 0. So what I'm left with then is exactly what we had before. Set then the corresponding derivative equal to 0, solve for pi, and of course you get then w divided by n as the maximum likelihood estimate. Okay, some important notes. Generally speaking, not always, but at least for how we're going to be examining maximum likelihood estimation in our class, we can simply always work with the derivative with respect to the parameter that we're interested in. Suppose theta is our general parameter that we're interested in. Take the derivative of the log likelihood function with respect to theta, set it equal to 0, solve for theta. That's going to be your maximum likelihood estimator or estimate. Now, what happens though if you have 2 or more parameters? Perhaps have a likelihood function that's written in terms of, let's say, theta 1 and theta 2, where theta 1, theta 2 are some parameters of interest. Then finding the MLEs becomes a little bit more difficult. In this case, you need to take the partial derivative with respect to each of the corresponding parameters of interest. So with respect to theta 1, I do that separately from doing it with respect to theta 2. Set these partial derivatives equal to 0. Solve for the corresponding parameters. So in this case, I have 2 equations, 2 unknowns. Then the corresponding solutions will be the MLEs. We'll have examples showing that shortly. Now, unfortunately, there are often times where a nice little solution, such as the sum of the y sub i's divided by n, cannot be actually written out, meaning you don't have necessarily a closed form expression for what the actual solution should be. And so what you need to do in order to solve for this theta, in this particular case, you need to use what are called numerical iterative methods to find the solution for your specific data that you've actually observed. So if you've heard of like a Newton-Raphson method, perhaps, that will be one of these numerical iterative numerical methods that one could use to actually find the corresponding solution. And this is a case, for example, like if you were to use the gamma PDF. Now, a simple way to do it when you don't have too many parameters is just to do what's called a grid search, where you look at a whole, in the case of a gamma distribution, you have a whole bunch of different values of alpha, you have a whole bunch of different values of beta, plug them into your log likelihood function, and then look which values of alpha and beta end up actually maximizing the corresponding log likelihood function. Okay, so let's take a look at an example. What we're going to try to find is the maximum likelihood estimators, or estimates, or MLEs, for mu and sigma from a normal distribution. So we're going to assume that y1 through yn is a random sample where a normal PDF can be characterized in the corresponding population. The expected value of y sub I is mu. The variance of y sub I is sigma squared. Okay, so here's our normal PDF that we've seen many times before. So to find the likelihood function, all I need to do is use this product notation again. We take the product from I equal 1 to n. Here's my normal PDF. Notice how I have a y sub I in there. And then we have a little bit of simplifications. So we can see that this essentially is a constant for all parts of that product. So I can factor it out. So now I have 1 over 2 times pi, and pi is the 3.14, that constant in this particular case. 1 over 2 times pi raised to the n divided by 2 power. And then also have 1 over sigma sub n. Then e raised to, and remember we're going to have to sum the items that are in the power there, negative 1 over 2 sigma squared times the sum I equal 1 to n, y sub I minus mu squared. If for some reason you don't see how I get between these two parts, please let me know and we can go through it. So let's take the log of the likelihood function and notice how things nicely simplify. So now I have negative n divided by 2 log of 2 pi. So notice I have an n divided by 2 there. That's where that comes from. The negative comes from, of course, that this was in the denominator. Then I also have negative n times the log of sigma. So it comes from there. And then lastly, because I have e here, notice how we have this really nice simplification. Now I just have negative 1 over 2 sigma squared times that sum. So of course, the natural log of e is equal to 1. Okay. Now, to find the maximum likelihood estimate here, I'm going to need to take the partial derivative with respect to mu, set it equal to 0. Then also take the partial derivative of the log likelihood function with respect to sigma, set it equal to 0. Let's first attack the mu part. So I take my partial derivative and notice that I have some terms here that do not have a mu in it, so they disappear. I'm just left with the part that has the sum in it. Now we have these constants out here. I can move those over to where you see the 0, and I'm going to take 0 times them, and therefore they disappear. So what I'm left with is just simply the sum of the y sub i's minus mu set equal to 0. Solve, and you get the maximum likelihood estimate for mu hat, to be simply y bar. That makes sense to happen. Sample mean is going to estimate the population mean, or that population mean parameter. Then, if I want to find it, I need to do that derivative with respect to sigma. And so this is what I get here. One of the terms that was in the log likelihood function disappeared because it's not a function of sigma. I set this equal to 0. I do some algebra then, and I get sigma hat to be the square root of the sum y equal 1 to n, y sub I minus y bar squared divided by n. And equivalently, sigma hat squared is then the sum y equal 1 to n, y sub I minus mu squared over n. And I failed to mention this. So you have a mu in there. So let's replace it with mu hat, or in other words, y bar. Okay. So you can see that when you have two parameters, it can be a little bit more difficult. And in this case, actually, it's not as difficult as it could have been, because to find the maximum likelihood estimate for mu, when I did that derivative with respect to mu, notice that sigma was no longer in the expression, so I can immediately solve for mu. Now, what's really interesting here is the MLE for sigma squared is not the unbiased estimator that we've been using for the sample variance to estimate sigma squared. That's quite interesting. So instead of having an n minus 1, the MLE actually just simply has n itself. Therefore, the maximum likelihood estimate in this particular case is what's called biased. Because if I were to take the expected value of sigma hat squared, I'm not going to get sigma squared like I did when I was working with s squared. But in the end, it's not a big deal, because notice as your sample size increases, this difference between this expression and this expression is going to become smaller and smaller and smaller and smaller. So even though the MLE is biased, it's not really a big deal for large samples. Okay. So maximum likelihood estimation. This is a commonly used method to find it's a commonly used general method to find estimates for parameters from a particular probability distribution.